Let's start the review with this question. We're told that online sales have been at record levels in the US in 2020. The information given shows the average spending per consumer in 2019 and 2020, along with the population standard deviation and the sample size for each sample. So we're given that data here in these cells. Then what we need to do is we need to perform a hypothesis test using a 0.05 level of significance to determine if the average amount of online spending has increased from 2019 to 2020. So the first thing that we're going to say here is we're going to use mu1 for 2019 information, and mu2 is going to represent our 2020 info. So that's step one here. Now, before we even perform a hypothesis test, we need to first find our hypotheses, right? So what we want to figure out here is if the average amount of online spending has increased, meaning that mu2 is going to be greater than mu1. So we're going to write it out like this. So mu2 is greater than mu1, which is the same thing as saying mu1 is less than mu2. So the reason that we want to write it out kind of backwards here is because in our hypothesis test, when we find our null and our alternative hypotheses, we are going to need our hypotheses to say mu1 minus mu2 is something. Right? So if we write it out like this, where mu1 is less than mu2, we can then turn that into mu1 minus mu2 by just subtracting mu2 from each side is less than 0. And this is our alternative hypothesis. So we plug that in here for our alternative hypothesis. Now remember, your null hypothesis and your alternative hypothesis are just the opposite of each other. So if the alternative is that the difference is less than 0, the null is going to be that the difference between our two means are greater than or equal to 0. So now we have our two hypotheses figured out. Now we just roll through the rest of our hypothesis test. So our alpha is going to be 0.05, that's our level of significance. Then we need to find our standard error. So the standard error formula is a little messy. It's the square root of each of the population standard deviations squared, divided by their sample sizes, and added together. So instead of trying to put that all in one cell, we are going to break it up into 4 different steps. So we have step 1, step 2, step 3, and step 4. So step 1 is going to be the population standard deviation from 2019 squared divided by the sample size from 2019. Step 2, we're going to do the same kind of thing except use 2020 data. So the population standard deviation from 2020 squared divided by its sample size. Step 3, we're just going to add those two together. And then step 4, we finally take the square root of that. And this 24.97, that is your standard error. So now that we have that, now we can find our test statistic and our critical value. So let's start first with our test statistic, or our z-test. So the way that we're going to find this is by taking the difference of our two sample means. So our 840 minus the 900, and we divide all of that by this standard error that we just found, the 24.97. So that comes back with this test statistic of negative 2.4. Then we need to find our critical value, or our critical z-score. And that's all associated with our alpha. So in order to do that, we take norm.s.inv for the inverse, just pop in the alpha of 0.05, and that kicks back this critical z-score of negative 1.645. So a few different things we can do here. We can compare the test statistic to the critical value. We could also just compare the p-value to our alpha. Let's first just work with our test statistic and our critical value here. So if we draw out a bell curve and we put our critical value here of this negative 1.645, that critical value sets what we are going to call the rejection zone. So anything over to this side that I'm shading in is the rejection zone, which means that if our test statistic falls within that rejection zone, we are going to reject our null hypothesis. Well, we see that our test statistic is negative 2.4, which does fall in our rejection zone. So we are going to say that we will reject our null hypothesis. So that's one way that we could figure out whether we need to reject or not reject the null. The other is to compare your p-value to your alpha. So the rule that we have is that if the p-value is less than or equal to alpha, then we reject the null. So the alpha, we already know, that is our 0.05. P-value, we need to figure out. To find the p-value, we take norm.s.dist of our test statistic, that negative 2.4, and then we type in true, and we see that the p-value is 0.008. So that is less than or equal to our alpha. So once again, we come out with the same conclusion that we need to reject the null. Now, just saying that you need to reject the null or not reject the null doesn't really explain what's happening here. So we want to also figure out what that conclusion means. So we take a look back at our null and our alternative hypotheses here. We're rejecting this null hypothesis. We are saying that the difference between the means is not greater than or equal to 0. Which means that the difference between the means must be less than 0. And if that's the case, we just had enough evidence to show that spending did increase from 2019 to 2020. Now let's take a look here at question number 2. Question number 2, we're told that lead companies trying to determine if there's a difference in the average wait times for customers at their 3 different stores. So the following wait times were selected throughout the past week at each of the 3 stores. So they have an East Valley store, a Central store, and a West Valley store. And we have our different wait times there. we need to perform a one-way ANOVA using a 0.05 level of significance to determine if there's a difference in the average wait times at the 3 stores. And again, we want to know if there's a statistically significant difference. That's a key here. So whenever we are working with this, we're going to have our null and our alternative again. Your null is just that the 3 different means equal, and your alternative is that not all of the means equal. So that's going to be your null and your alternative here for this ANOVA. Now, how are we going to figure out the rest of this, right? Well, the ANOVA is found under your data analysis. So we need our data here. We hit data analysis and we come up to ANOVA single factor, asking for our input range, which is going to be our data here. It is grouped by columns. Labels are in the first row, the East Valley, Central, and West Valley. And our alpha is 0.05. So where do we want it? We'll say that we just want it right there. And we hit OK. And we have our ANOVA output here. So what we need to figure out is whether there is a difference or not. So they give us our averages here. So we can see that the average wait time for the East Valley store is a little bit more than 14 minutes. The Central store is a little bit more than 15, and the West Valley, it's an average of 13 minutes. So there is a difference in these samples. But again, what we're trying to do is we're trying to use these samples to figure out for all of the wait times at these stores, is there a difference? So there needs to be a big enough difference between all of these averages for there to be a difference in our true population means. So what we're going to do here is we are going to compare a few of the different numbers given to us in this output. We're going to take a look at our F that we're given and compare it to the F critical. So our F that we are given here is this 0.3275. The F critical is this 3.55. Since our F is less than our F critical, it does not fall in the rejection zone, and we are going to say do not reject the null. So using this test, we are saying that there's not enough information to say that all 3 of these means are not equal. Even though the sample means are all different, there's not enough here to say that the population means aren't all the same. Now we could also use our p-value test here, right? So the p-value has to be less than or equal to alpha. And if that's the case, we reject the null. Well, our alpha is the 0.05. That's our level of significance. Our p-value is given to us right here, the 0.72. Well, our p-value here is very much greater than our alpha. So once again, we come back with this same conclusion that we do not want to reject the null hypothesis. We need to now figure out what that means. Because just saying reject the null or do not reject the null doesn't explain what's happening. So if we are not rejecting the null here, that means that there's not enough evidence to show that the wait times between the 3 different stores are different, right? So there's not enough evidence showing that the wait times between our 3 different Valley stores are different. There is a difference between the sample means, but it's just not significant enough. Now, question number 3. Question number 3 says that the manager at ABC Retail is scheduling staff for the holidays. So the information below was gathered from the 2019 holiday season. We have the number of employees that were staffed, and then the sales per hour when those employees were staffed. So we have 4 different pieces that we need to find here. We first need to figure out the regression equation. Then we need to find the coefficient of determination and the correlation coefficient. And then we need to solve for a few things. First, if the manager schedules 20 employees, how much in sales should the manager expect to make? And then, how many employees should the manager schedule to make at least $300 in sales per hour? So the first step here is going to be to create this scatter plot. So we will select our data, go to Insert, and create this scatter plot here for our data. Now there's a few different things that we are going to want to add onto this. We're going to want to add a trend line. So that trend line, that dotted line that we see, that's our regression line. So step A, part A of this problem, is to find the regression equation. So in order to find the regression equation, we will right-click on our trend line and hit Format Trend Line. And then all of this information comes up over on the right. We'll hit Display Equation, and let's also display our R squared. So now we have that information at the top of the scatter plot. So that y equals 13.996x plus 99.28, that's our regression equation. That's the equation of that trend line. The R squared, we're going to see that pop up somewhere else too. So now we need to find the coefficient of determination and the correlation coefficient. The best way to do this is to use our data analysis. So we need our data analysis, and we are going to be using our regression here. So it's going to ask for the y and the x. So the x produces the y, right? The y is what we are trying to find here. So the y is our sales per hour. The x is the number of employees staffed. Because the number of employees that are staffed determines how much in sales we are making per hour. So we do need to say it has the labels because we did select the number of employees staffed and the sales per hour. It's going to ask for an output range. We'll just have it pop down there. And then we hit OK. And we are given our regression output. So a few different pieces here are important. We can see the R square. The R square is the same number that we have up here on our scatter plot. That is our coefficient of determination. That is telling us how well this trend line, this regression line, fits our data. So we want a regression to come back with an R squared of a number as close to 1 as possible. Here, 0.95, that means that our regression line fits pretty well. So we're good here. Now, we also needed to find the correlation coefficient. Few different ways that we can do this. Correlation coefficient is the square root of the coefficient of determination. So if we took the square root of that 0.95, we get 0.97597. Where else do we see that? Right here with multiple r. So the multiple r is going to be your correlation coefficient. If you forget that, you can always just take the square root of that r squared. Then we take a look down here. This 13.996, the coefficient for the number of employees staffed. This number is going to be your slope. We can look again at the equation of the line that we have up above. 13.996x. That's the slope times your x value. So this amount in this regression output is going to be your slope. This 99.28, that's your y-intercept. Once again, that number matches what we have above with the equation of that regression line. These two cells that I just highlighted here, this really, really small value, this is your p-value. So if you need your p-value in a problem dealing with regression, this is where you could find that p-value. Now, this question is also asking, if the manager schedules 20 employees, how much in sales should the manager expect to make? So that's the beauty of using regression. Regression can help you predict. So your number of employees, we said that that was our x variable. So if your x equals 20, we are trying to figure out the number of sales in that hour. So we're solving for y in our regression equation. So our regression equation, remember, is 13.996x plus this 99.281. So then we just need to plug in 20 for that x. So y equals 13.996 times 20 plus 99.281. We'll toss an equal sign at the front of this. And we can see that the number of sales per hour that the manager can expect is a little bit more than $379. So that is just forecasting out this regression line to say if it goes all the way to where your x value is 20, somewhere over here, this would go all the way up to $379. Now, a manager might find that information useful, but another way that a manager might look to schedule employees is saying, I want to make at least $300 in sales this hour. How many people do I need to have on duty? How many people do I need to have in the store right now in order to make $300 in sales this hour? So instead of solving for your y, in this case, you're going to solve for your x. So it's a little bit trickier, right? So we don't know our x. Our x is our number of employees. Our y is our $300 because we want to make $300 in sales this hour. So what are we going to do? Well, we're going to set it up again using our regression equation. So we have our regression equation here where the y equals our slope times x plus our y-intercept. Now we know that our y equals this 300. And we're solving for x. So we set it up like this. So we need to get x by itself, right? We need to treat this like an algebra problem. So we will take 300 minus 99.281, and that's going to equal our slope times x. So then to get x by itself, we need to divide each side by our slope. So if we take this 200 divided by 13.996, we get our x value. So in order to make $300 in sales, this is the number of employees that we need. Now, if you're the manager, you can't staff a third of an employee. So whenever you see something like this, you would then need to realize that we need to staff a 15th employee. So we need 15 employees in order to make $300 in sales per hour. So the manager would need to schedule 15 employees because 14 wouldn't be enough. Now we come to our last question, dealing with these X bar charts and R charts. We have this information here that says that a company has collected 5 samples with 4 observations each. And we need to find the upper and lower control limits for the X bar and the R charts, and then we need to actually construct those charts. So the first step when you see a problem like this, it would be good to find out what your N is and what your K is. All along in this class, N has always represented your sample size, right? How many pieces of data are in this sample? Same idea here. So if we take a look, we have 5 different samples, but in each sample, we have 4 observations. So your N is 4. Your K is your number of samples. So that's where we're interested in these 5. And why this is important is because when we need to use these constants down here from our control charts, we need to know what our N is, because we pick which constant we're going to use based off of our sample size. So now we can work on figuring out how to build these charts. So we have our information here. It would be good to then figure out our X bars and our ranges. So the X bar is just the average of each sample's observations. So we find our averages here. R stands for range. Now, there isn't a specific formula in Excel for the range. But if we think back to what we learned earlier in the semester, ranges are just the max minus the min, right? So we take the maximum number from our sample and subtract out the smallest number, or the min, from that sample. So we can find all of our ranges for our 5 different samples. Now, once we have those, we are going to need what's called X bar bar, or the mean of the means, and the R bar, or the mean of the ranges. So X bar bar is the average of our 5 different averages here. And R bar is the average of our 5 different ranges. So now that we have these values here, we can now think about creating the upper and lower control limits for the R bar chart and the R chart. So let's first just talk about the equations that we're going to use. So for the X bar chart, we have an upper control limit and a lower control limit. For the upper control limit, we are going to use X bar bar plus A2, which is going to be a constant over here, times R bar. The lower control limit, we just toss in a subtraction, but everything else remains the same. And then when we have the R charts that we're going to build, our upper control limit is going to be D4, which again is a constant that we'll find, times R bar. The lower control limit is D3 times R bar. So that's why we need this chart when we are creating the upper and lower control limits for the X bar chart and the R chart, because we need to be able to figure out these constants that we'll have in these formulas. So now let's create the upper control limit, lower control limit for the X bar chart. So the A2 that we're going to have here in this formula, we find in this chart. Our sample size we see as 4. So we come to this chart, we see that our sample size is 4. The A2 that we want is 0.729. So let's put that into a cell that we can reference. Now, when we create the upper and lower control limits here, what we're trying to do is make it so that way when we plot this all in a scatter plot, it will create a line. So our upper control limits are all going to be the same number. Lower control limits are all going to be one specific number. And then we'll just put our R bar value in there in each of these cells as well. And then that way, when we plot them on a scatter plot, we can create straight horizontal lines. So when we do that, we're going to want to make sure that all of our cells are frozen in these formulas. So for the upper control limit, we want our R bar bar, which is this 3.495 that we found. We freeze that. And we add our A2 that we found. We'll freeze that, multiply that by the R bar, the 0.96, and we freeze that as well. So that comes out with our upper control limit of 4.19. Now we want to drag that down so that way we have 5 of these, and that will make a little bit more sense once we create the charts themselves. Now we do this for the lower control limit. So R bar, we freeze it, minus A2 frozen times R bar frozen. And we get a lower control limit of 2.79. So we pull that down as well. And then we want the X bar bar in here also. So we'll just select this cell, freeze it, and then we have all of these for the X bar chart that we're going to create. Now, before we create any of these X bar charts, let's also figure out the upper control limit and the lower control limit for the R chart. So our formulas down here show that we need two other constants, right? We need our D4 and our D3. So let's start with D4. D4 we get from this chart again. Our sample size we said was 4. So we bring that across, and we're going to use this 2.282 as our D4 constant. Now D3, so our sample size is 4. We bring that across, and we see that D3 is just going to be 0. Now we will use our formulas that we have here to find the upper and lower control limits. So our upper control limit is D4, and we want to freeze that. Multiply that by the R bar. Once again, we want to freeze that as well. So we get our upper control limit for the R chart of 2.19. Now, lower control limit, we take D3, we freeze that, multiply it by R bar, which needs to be frozen, hit enter, and it's just going to be 0 because our D3 was 0. Now R bar, we just want to select that, freeze that cell, so that way we can have 5 of those listed here. Now we have all of the pieces to finally start creating the X bar chart and the R chart. So when we do this, we are going to want to select our samples, our X bars, and all of our upper, lower control limits and the X bar values here. So if you hold down Control while doing that, it will select all of these values. Then we come up and we hit Insert, and we'll want to hit our scatter plot. Now, you'll notice this doesn't really look like a X bar chart. So if something like this happens to you, you come over here and you hit the chart filters. You hit Select Data, and you'll need to switch the row and the column. And now things look a little bit better, but still not perfect, because we have all of this blank space down here. Well, if you have a bunch of blank space down here, that means that we can reformat the y-axis. So we'll format our axis. We'll put our minimum at about 2, hit enter, and now the X bar chart's looking a little bit better. All right, so let's title this X bar chart. Now, we aren't done yet. What we need to do now is format our upper, lower control limits and our X bar. So if we tap on our upper control limit here, it'll select all of these different data points. And we are going to want to format the data series, come over to the line, and say that we want a solid line. So let's make that just a solid red line. Then we also want to eliminate all of the markers, all of the individual data spots. So in that way, our upper control limit is just a straight line across. We're going to do the same thing down here for the lower control limit. So we want a solid line, and we don't need any of those markers. So now we have our upper and lower control limits. We'll do it for our X bar. In this case, we're going to want a different color. So let's just use green here for the X bar line. And we will get rid of all of those markers. Now this is a little bit easier to look at, to understand, right? We have our upper, we have our lower control limits. These blue dots are all of our X bars. If any of these blue dots were either above or below our control limits, the process would be out of control. They are all within the limits, however, so the process is in control. So now we can move on and create the R chart. So to create the R chart, we're going to follow a similar pattern to what we just did for the X bar chart. Select our sample, select the R's and our upper and lower control limits. Insert a scatter plot. We're going to need to flip around our rows and columns again. And we now have an R chart. Now we need to format our upper and lower control limits, so then that way we have the straight lines again. So we want a solid red line, and we want to eliminate the markers. So in that way the upper control limit's just a straight line. Lower control limit, we want another solid red line, and eliminate the markers. And then the R bar in the middle, we want a solid line, but we're just going to go with green so that stands out from the control limits. And once again, we want to eliminate the markers. So we can now take a look here and see all of these individual blue dots. Those are all of our ranges that we see here over in column G. So if any of these blue dots were above the upper control limit or below the lower control limit, we would once again be out of control. But since they are in between the upper and lower control limit, we can officially say that this process is in control.